Welcome back to the course on basics of modern control system. As I said in the previous lecture, there will be three parts to the course: the linear algebra, then the linear systems, and then the non-linear systems. For this course, I'll be using the following references or referring to the following books. For the linear algebra part, I'll be referring to Finite Dimensional Vector Spaces by Paul R. Halmos. For the linear system part, I'll be referring to two books. One is Linear System Theory by Wilson J. Roth, and another is Linear System Theory and Design by C.T. Chen. For the nonlinear systems, I'll be again referring to two books. One is Nonlinear Systems by H.K. Khalil, and another is Nonlinear System Analysis by M. Wilson. Apart from these five books that I'll be referring for these books, there are other books as well which one can refer to for linear algebra or linear system theory or nonlinear system theory. Essentially, the concepts that we will be covering in this course are going to be the same no matter which book you refer to. You can also refer to these books and other books to take up examples or some practice problems. And towards the end of this course, we will try to see if we can take up some examples and apply them to the same book. Let's see how far. Okay. So, what is this course aimed at? So, this course aims at introducing some basic tools needed for the time domain analysis for linear and nonlinear continuous time systems. Okay. So, what we'll be seeing is basically how to do the stability analysis for any of the systems which are either linear or nonlinear but continuous time. We'll also see some concepts of controllability, causability, and we'll also see methods to design controllers or estimators for such systems. Okay, what exactly do we mean when we say a system? System is essentially a meaningful interconnection of components which, when subjected to an external input or some internal condition of the component, results in an interaction of these components, and this interaction results in a response which we call as output. Okay. Now, when I say external input, it essentially means a stimulus that has originated outside the interconnection of these components that comprise the system. And when I say internal condition of the system, it is something like, for example, in RLC circuit, the charge that is already there in the capacitor, basically the energy that is already there in the storage elements. Okay, so or in a spring mass damper system, let's say that the spring is already stretched. So those are internal conditions. So here the component is basically the spring. Okay, that's spring mass damper system. Similarly, in the RLC circuit, the component is the capacitor and the inductor, and the internal condition is basically the energy stored in them. Okay. Now, you can have components, but they have to be interconnected meaningfully. So, so once they are interconnected, you give an input. This input will affect the components, and these components will start interacting with each other directly or indirectly, and will result in a response to these inputs. Okay, the external input or the internal input. Okay, it can be both as well. For example, you have at some point of time come across permanent magnet brushed DC motors. Okay. They're usually found in toys, electronic toys, battery operated So we'll term this as a PMDC motor. Okay. So what are the components that are there in this permanent magnet DC motor? The components that you find in this permanent magnet DC motor is, of course, as the name suggests, a permanent magnet pair. Okay, so in those small DC motors, you would see two magnets. One face would be acting like the north pole, and the other face would be acting like the south, roughly. Okay. You have this. Then you'll have armature winding on the rotor. The rotor is basically the part of the motor which rotates. Okay, so the rotor comprises of winding. Basically, there are coils of conductors wound in a particular way, and we call this as the armature. Okay, you have this. Then you have a commutator. Commutator is the part to which the terminals of the windings are connected. Then you have brushes. Brushes connect the commutator to the terminals. Okay. So when you apply a voltage, okay, across the terminals, if I draw it, it would be, let's say, something of this form. You have the commutators, and then you have the brushes, and this serves as the input terminal. So this guy here is the coil. The coil is connected to the ends of the coil are connected to the commutator, and the commutator are connected to the brushes. So when the coil rotates, the commutator keep on changing brushes. Okay. Now when I apply voltage across these terminals, current flowing, there would be a current that will flow through this coil. This flow of current will interact with the magnetic field and will experience a force. That force will lead to what? Motion of the coil, which is basically a rotating motion. Okay, and this goes on. So what you essentially have is the rotor of the motor starts rotating. Okay, so here the external input is the voltage that is applied across the terminal. The components then start interacting, and once they start interacting, the response is the rotation of the rotor. So the input here is the voltage applied, and the output or the response is the rotation of the rotor or the speed of the rotor. Okay. So now you can also mark, let's say, a point on the shaft of the rotor. Okay, and you might be interested in tracking the position of this particular point as the rotor rotates. As time progresses, as the rotor rotates, you might be interested in basically tracking that particular point. So the output now becomes the position of this particular mark. Okay. So output of a system is basically a quantity of interest that is being affected by the interaction of the components due to the external stimulus or the internal conditions of the component. Okay. Output is something that is of interest to us. Okay. For example, if you consider a spring mass damper system, let's say we have a mass connected to a damper. Let us have a bigger mass so that I can draw a spring. And a spring is the direction of motion, and let's say this is the force acting on it. Okay, so here y denotes the displacement of the center of mass of this particular object that is being subjected to the force, and y dot denotes the velocity. Okay, now here one may be interested in how the velocity of the mass changes as the depending on the force that is being applied on the mass. Okay, so hence the output that we'll have for the system is the velocity for the input force. For the same force, one may also be interested to look into how the position of the center of mass changes. So now here for the input F, the output is the displacement, okay, or the position of the center of mass. And in some case, one might be interested to look into both the position and velocity of the center of mass under the effect of this particular force. So the output is now a vector, okay, or there are two outputs that we are interested in. One is the position and one is the velocity of the center of mass. Okay. So output of a system is basically a quantity of interest or quantities of interest to us, because there might be certain objective that is supposed to be fulfilled with respect to the output. And so these are quantities of interest that are affected by the action due to the external stimulus or the external input that is there, or the internal condition. Okay, so example again coming back to the spring mass damper system. Suppose the at time t equal to 0, you know that the mass has been pulled so that the spring is stressed. Okay, at t equal to 0, you release the force. So basically, the internal condition is the spring is stressed and the damper is also in action. At t equal to 0, when we remove the force, that is where we see how the system is evolving due to the internal condition, that already stressed spring and damper already activated. Okay, so how the position vary, basically how the energy from the spring and damper will be released out, and the position and velocity can vary. Okay, so there has to be some way in which we can express or find a relationship between the output and the input, okay, or the output and the internal conditions. Often, the relationship between the input and the output of a system are represented by algebraic and or ordinary or partial differential equations. Okay, so the relationship between the input and the output of a system can be represented by algebraic and or ordinary or partial differential equations. Okay, so you can basically relate the input and output to a set of algebraic equations only, or through a set of algebraic and ordinary differential equations, or through a set of algebraic and partial differential equations, or through a set of ordinary and partial differential equations and algebraic equations. Okay, I mean, for something known as memory-less systems, only algebraic equations are sufficient to establish a relationship between input and output of the system. Why? Because in case of these memoryless systems, the output depends only on the current input, okay, and does not depend on what was the output previous at previous instance of time, or what was the input at previous instance of time, and so on, or how the input is varying, or how the input has varied. Okay, it depends on what is the value of the input at this instant of time. The output depends on what is the value of input at this instant of time. It can be a non-linear or a linear equation. Okay. So we'll go through this what a memoryless system is. Okay. Now, if there are something known as memoryless systems, then there are systems probably which are memory. Now, for systems with memory, the relationship is described by differential equations and algebraic equations. Okay. Differential equations. So what we'll be dealing in this course, if it's a memory-based system, then it will be basically ordinary differential. Then it should be represented with ordinary differential equations and algebraic equations. So we'll only study those systems. So now, what are memory-based systems? Basically, the output would depend on how the output was in the past, and how the input has been varying, and how the input was basically in the past, or sometimes how the input is going to be in the future. Probably. Okay. Example of a memory-less system: a purely resistive circuit. So let's say that you have a resistor R. The input here is the voltage that is applied. So this is the input. The output is the current that flows in the circuit. Now the current that flows in the circuit by Ohm's law is voltage applied divided by the resistance. Right? So if you notice, the current at any instant of time depends on the voltage that is applied across the resistor at that instant of time. Does not depend on what was the voltage previously, or how the voltage has been changing, or what was the current that is flowing through the resistor previously. Assuming that the resistor R resistance R does not change as time progresses. because normally the resistances would change, right? As current flows due to heating, the resistance can increase. Okay. Yeah, assuming that for a sufficient length of time, resistance does not change. So in such case, the current that flows through this circuit, a purely resistive circuit, depends solely on what is the voltage that is being applied at that instant. Okay. So I should, to be correct, I should write I of t, the t denotes the time, depends on V of t divided by the resistance R. Example of a memory based system, you can take the example of this spring mass damper system that we had been discussing. How the position of the center of mass changes depends on what was the state of the spring and the damper previously, how the force has been varying. Okay. Similarly, for RLC circuit, a series RLC circuit with voltage as the input and current being considered as the output, the output depends on what was the energy that was already there in the inductor or the capacitor. Okay, how the voltage is varying. So in this case, I have considered DC source. You can consider in general any voltage source that can be. It can be a varying voltage source, alternating voltage source, or any other voltage source. It can be a voltage source which is basically looking like a pulse changing between 0 to 5 volts at a certain frequency. It can be this as well. Okay. So I can possibly represent it like this. Okay. So the current depends on how the voltage is changing, what was the state of the inductor and capacitor in terms of the energy stored in them, and so on. So the RLC circuit is also an example of a memory-based system. Okay. So the dependence of the input-output, so the relationship between the input-output and the dependence of the output on the history or possibly future of the input and the internal conditions of the system helps us in classifying the system into two parts, right? Memory-less systems or memory-based systems. This brings us to the fact that there are possibly other factors over which we can classify systems. Okay. One was, of course, depending on whether the system has memory or not. We classify it as memory-less or memory-based. Okay. Right. This is a memory-based system. Okay. So I will briefly outline what are the classifications that one can have. We'll start with the first one, which is for a system, how many inputs and outputs are there. Number one, You have single input, single output systems. You have multi input, multi output systems. Single input, multi output, multi input, and single output systems. Okay, so there are four classifications that one can have. The next set of classification that you'll have is type of input and output signals. So one can classify them as continuous time system. The input and output signals are continuous. And discrete time system. Input output discrete. The next classification is outputs dependence on past, present, and future inputs. Depending on that, we have a causal system where the current output depends on the past and the present input signals. Okay, so it basically means that if there is a cause, there would be an effect. Okay, a non-causal system where the current output may depend on past and present, but definitely depends on future inputs. Okay, so these are non-causal systems. The output depends also on the future inputs. The next classification is something that we have already seen, is based on memory. You either have memory-less system or you have a memory system or a memory-based system. Okay. Now, memory-less system output depends only on the current input. Memory-based may output may depend on the past or on the future, but it is for sure that output does not only depend on the present. Okay. The next classification is based on linearity. If a system is linear or satisfies the principle of superposition, then we call it linear system. So basically, for input, let's say u1, the output of the system is y1, and for another input u2, the output is y2. Then if you scale up the input u1 and the input u2 and add this scaling, then the output that you get is a scaled version of the corresponding inputs summed together. Okay, so this is the linear. The linear systems obey this. Systems which do not obey this will be termed as non-linear systems. The next classification is the outputs dependence on time. So basically it means the output not only depends on the input but also depends on when the input is being applied. Okay, so you have time invariant system, which means if a input u is resulting in output y, then a time shifted version of the input, or if an input is um, applied after a certain amount of time, or rather I should put it like this in figures, it would be better. So this is u and this is y. So let's say that for a u like this 0, the output y was this. Okay, now for this system, instead of starting at t equal to 0 or applying the input at t equal to 0, what you do is, so this is 0 again, this is u, this is y, this is the time axis. You start at a different time with the same input, but start giving the input at a different time. Then what you observe, that the output looks similar to what you had, looks same as what you had previously, except for it is just a shifted version, and it is shifted by the amount u has shifted. Okay, so it doesn't change. So it really doesn't matter when you apply the input until the input applied is the same. Okay, so whatever input you applied at this point of time, if you get some output, we apply the same input under same internal conditions for the system. Let's say 1 hour later, and the output that you get is same what you would have got now, then the system is time invariant. If that does not happen, then the output changes because you applied the input at some different point of time, then we call that a time varying system. Okay. The next classification is deterministic or stochastic systems. So deterministic systems produce the same output for a given input. Okay. And you exactly know that if this is the input and this is the internal condition, then this is exactly what the output is going to be. So for the knowledge of the input and the internal conditions, you can exactly say what the output is going to be. For a stochastic system, for the same input and same internal condition, it probably would be generating different output. So you can say that with the probability of this, that the output is going to be something of some sort. Okay. So it's, I mean, you cannot exactly say that this is the output that we are going to get at every whenever you apply the same input. So in this course, we will be handling deterministic uh, systems, and the last classification is lumped or distributed systems. Okay. We call the system to be lumped if we have finite number of state variables and distributed if we have infinite number of state variables that will given the behavior of the system or the user. So through in this course, what kind of things we'll be dealing? We'll be dealing with in some point of time we'll be dealing with all the type of systems that are defined by the number of inputs and number of outputs. But we'll be mostly dealing with continuous time systems that are causal. They will be memory systems. They can be memory or memoryless systems. They and will be, as I said, we'll be focusing on both linear and non-linear systems. Time, these systems can be time varying or time varying, but we'll be dealing with primarily deterministic systems and lump systems. We'll focus on causal deterministic lump linear or linear time varying or time varying systems with continuous time input and output signals. Okay. So to proceed further, what we'll do is we'll start with the part of linear algebra that we will need for this course. And once we cover the topics required for this course under the linear algebra, we'll move into linear systems. Once we have seen different, once we have explored linear systems, we will go to nonlinear systems and we'll see how nonlinear systems vary from linear systems. Not only as a property of non linearity not holding for nonlinear systems, but are there any other things that are special to nonlinear systems that cannot be found in linear systems? It might be good as far as the nonlinear systems go. So we'll carry on in this with the next lecture. Thank you.